In this video, I'm going to use mathematical induction to prove a formula for the addition of cubic numbers. Now I'm going to prove that 1 cubed plus 2 cubed plus 3 cubed plus plus n cubed is equal to a quarter of n squared n plus 1. And I want to show that this equation works when n is greater or equal to 1. Now, you can get a feel for this formula by inputting some numbers as n, and you can kind of get a feel for whether it works or not by doing that. But I'm going to use a technique called mathematical induction. So for mathematical induction, the first thing that we need to do is prove the base case. And this is the case when n is equal to 1. So what we can do, we can insert 1 into this above equation. So we can show that 1 cubed is equal to a quarter of 1 squared times 1 plus 1 squared. Now, 1 squared is 1, a quarter is just a quarter, and 1 plus 1 squared is 2 squared, which is 4. So that means 4 times a quarter is equal to 1. So you can see for the base case, this formula works. 1 cubed is equal to 1. Okay. Now for the next step in mathematical induction, we need to assume that k is equal to n, and then show that when n is equal to k plus 1, we get the same equation. Okay, so obviously when we get the same equation, we'll get the same equation, but we'll have an extra term. So obviously with k, when k equals n, we're just going to have that equation when k is equal to n, which will just be the same as this equation up here with k in it. Now, when we've got k plus 1, we'll have this equation up here, but instead we'll be substituting k plus 1 into n. So we will have the same equation, but with an extra term on it. So the first thing we'll do is first we'll assume that k is equal to n, and we'll find out what this equation is here. So when k is equal to n, we'll have 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed. And we'll find that this will equal a quarter of k squared times k plus 1 squared. Now we can work out what this equation would be if we had an extra term added in. So say if we were going to assume that n is equal to k plus 1, we would have an extra term. So if we had an extra term, we would have 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed plus k plus 1 cubed. So it's exactly as we had before, but we've got an extra cubic number, and that's k plus 1 cubed. Okay, and because this chunk here is the same as this chunk, we can then say that this new equation is equal to a quarter of a k squared, k plus 1, and this accounts for this part of the equation, because these two things are the same. And then we also need to add on our plus k plus 1 cubed. Okay, so this equation here is one of the ones that we need to use to prove our induction. Now, the next thing we need to do is we need to substitute our k plus 1 into our top equation. So now we can say that 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed plus k plus 1 cubed is equal to, and we're going to, this time, instead of adding on this extra term, we're just going to substitute k plus 1 into our top equation. So we're going to say a quarter of k plus 1 squared times by k plus 1 squared. And what we're going to do is we're going to simplify both this and this and prove that they are the same thing, and that will be enough to prove that our top equation works for all numbers of n greater than 1. Okay, and this relies on the domino effect. So what we're going to do first is we're going to expand our equation 1, the right hand side of equation 1. So if we start with equation 1 and expand this, we will have a quarter of a k squared, and then we'll have k squared plus 2k plus 1 plus we'll have, for this one we will have k cubed plus 2k squared plus k plus k squared plus 2k plus 1. And now if we are to simplify that, we get a quarter of a k squared 2k plus 1 plus k cubed plus 3k squared plus 3k plus 1. Now we want to join both this side and this side together. So the way that we do that is we expand the brackets, so we get k squared times each of the terms within this brackets here. So we get k to the 4 plus 2k to the 3 plus k squared. And then for this other one, to make it like this first one, we need to times each of the terms within the brackets by 4. And that allows us to put a quarter outside of the brackets. So then we get 4k cubed plus 12k squared plus 12k plus 4. And now we can add both the right hand side and the left hand side of the equation together. And this makes a quarter k to the 4 plus 6k cubed plus 13k squared plus 12k plus 4. And now we've simplified our equation 1 as much as we can. So now we're going to simplify equation 2. So equation 2 is quarter k plus 1 squared k plus 2 squared, because 1 plus 1 is equal to 2. Now if we expand these brackets, we get a quarter k squared plus 2k plus 1 times k squared plus 4k plus 4. And then we multiply each of the terms in the left-hand bracket by each of the terms in the right-hand bracket, so we get a quarter. So we get k to the 4 plus k 4k cubed plus 4k squared, and then we get 2k cubed plus 8k squared plus 8k, and then we get k squared plus 4k plus 4, and then if we simplify that, we get k to the 4 plus 6k cubed 6k cubed plus 13k squared plus 12k plus 4. And you can see that our equation 2 is now the same as equation 1. So quarter times k to the 4, 6k to the 3, 13k to the 2, 12k plus 4. Therefore, we've proved that 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed is equal to a quarter of n squared times, in brackets, n plus 1 squared by mathematical induction.